Okay, everyone, let's get started. So, as usual, for those of you watching on YouTube, if you can't hear or are having any issues, just paste something in the chat. So today's topic is language modeling. We'll be focusing on a very simple class of language models called n-gram models. And then we'll also discuss how to evaluate these models towards the end of the class. So before we get started, just a reminder of your impending deadlines. So February 17th, you have two things due. So first is your homework 0. I think I added all of you to the grade scope. If I did not, then send the instructor's account an email. Also, all of you should be on Piazza as well. If you just added or dropped, then send us an email and we'll add you to these things. Also, by February 17th, if you would like to form your own final project groups, you should submit a list of the 4 names of the people in your group as well as their email addresses. And if you don't elect to do that, we will randomly assign you to a group. Finally, about a month from now, the project proposals are due. So you should be thinking during this time, as soon as you form your group, about what kind of topic you would like to pursue in your final project. Okay, I also wanted to say that this semester, there's a way for you to earn extra credit. There's a weekly remote NLP seminar every Tuesday from 11:30 to 12:30. If you attend one of these talks and submit a short summary of its content, you'll receive extra credit. You can do this up to 3 times. The exact, questions that you'll need to fill out will be released later this week. There is one talk next Tuesday that will be the first chance that you can actually earn extra credit from. And that talk is going to focus on decoding from language models. So we will cover at a very basic level what that means today, and hopefully you can have some sort of understanding if you choose to attend this talk of what is actually going on. The talks will be recorded, so if you can't attend them remotely during the time that they're happening, you can also watch them later. Okay, so I will put details and Zoom links to all of these things in Piazza for you to follow along. All right, any questions about admin or deadlines or anything like that? Okay, so let's move on to the topic of today's lecture, which is language models. So before we jump into it, I just wanted to motivate why we are studying this problem again. I spent basically all of last class focusing on language models and showing you some of the cool things that they can do. But we're going to talk about a very primitive form of that model today. So it's important to know why we're learning about this and how we're going to extend it into much more complicated models later on. So the example that I was talking about from last class was sentiment analysis. So you have a review of some like movie or food or something like that, and you want to know whether the content of the review is positive or negative, right? This is obviously a problem that many different companies care about. They want to know what people are saying about their products. Just review from last time. In the past, how I would solve this problem of sentiment analysis is collect a large data set of reviews paired with the scores that the authors of the reviews assign them. And then I would train a model using supervised learning to, given the text of the review, predict the score. So this was basically the model only got access to sentiment data. It never had access to any other sort of data. The model that you end up with at the end of this process can only do sentiment analysis. It can't do anything else. So it's quite limited, but this was what people were doing until just a few years ago. So then we also talked about transfer learning yesterday. So in transfer learning, what happens is you have a pre-training stage in which you first take a model, you give it a bunch of unlabeled data. So this is not just sentiment reviews and scores, but it's any sort of text that you can get your hands on. And we discussed briefly last class how we can take some huge amount of unlabeled text and turn it into a supervised learning problem for a language model, where essentially you give the model part of the text and ask it to predict the next word of that text, right? And so if you wanted to do this task, you just need to collect as much data as you possibly can, and then you can arbitrarily create examples of this task for your pre-training. So once you do this and you train a model to predict the next word over a huge amount of text, you can then specialize the resulting model to any task of your choosing. So if you wanted to do sentiment analysis, you might collect a much smaller set of reviews and fine-tune your model that you pre-trained in the first stage on this smaller data set of reviews. So fine-tuning essentially means you are updating the parameters of your language model that have been pre-trained to predict the next word, such that you're adjusting those parameters so that they do a better job of predicting the sentiment rather than predicting the next word. The key concept of transfer learning is that you can take that same base model, the one over here, which you get from pre-training, and you can use it, you can specialize it to solve many different tasks. So this base model enables you to solve, like basically share a lot of information across many different tasks. The point of the base model is that it understands some general properties of the language, like that could be useful for all sorts of text-based tasks. So you're not just forcing this model to learn all about language just from a small set of Amazon reviews. Okay, and then finally, to recap last time, we also discussed this newer approach of just prompting the base language model to solve a task instead of doing any sort of training or fine-tuning on the sentiment data. So in this setting, you take your giant language model, and then instead of actually updating its parameters any further to specialize it for some sentiment task, you instead will just tell it in natural language, say in this case in English, what task you want to solve, how you want to solve it. You might give it some examples of that task, again in plain natural language, and the model should behave accordingly. So in this example, I want to use this model for translation. So again, this is a giant language model. It's only trained to predict the next word. How do I use this for translation? Well, in the simplest case, I can just say, translate English to French, give it a couple examples of the format in which you would like to do this translation. So you can see sea otter, peppermint, plush giraffe are paired with their French translations here. And then I give it the word that I actually want to translate, which is cheese. And I am asking it at this point to predict the next word, right? This is the task that it was actually trained on, predict the next word. The hope is that the model can learn from the examples that I've put in the prompt what should go in the next word, which is actually the translation of cheese into French. So we will spend a lot of time talking about these kinds of prompt-based methods. They appear very straightforward, right? Maybe you don't even need any sort of knowledge of how a language model works in order to write a natural language prompt and put it into the language model. If you have used ChatGPT, you don't know, you don't necessarily need to know anything about how that model works, but you're still able to, iterate over different prompts and figure out which prompts are best suited for which target outputs. So in this class, we will also talk a bit more about how this base language model is even capable of understanding instructions like this that are specified in natural language. Interestingly, compared to the last time I taught this class, there have been many more developments in our understanding on why this actually works. So we will cover that later in the semester after we've gone over the basics. Yeah.
So with prompting, we're not updating the weight of the model. It's just in the context of that particular
That's right. So with prompting, we are not updating the weights of the model to specialize it for, in this case, translation. We are just giving it input text, and it's asking it to predict the next word. So this is all part of the input text. If we wanted to do sentiment, we might just say, what is this sentence positive or negative? Maybe give it a few examples and do the same thing. All right, so that's the motivation. Now, oh, yes. The question is prompting, does it amount to finding the best way to formulate the task so that the model understands it? We will talk about this more because there are different ways to prompt the model. Here, I've just shown the simplest way, which is to do it in natural language. You can also let the model itself figure out what the best prompt is. And oftentimes, this doesn't correspond to anything that is interpretable in natural language. So there are like a lot of weird cases here that we will cover later on in the semester. At some point, humans can only do so much in formulating a prompt. They don't have any insight into how the model actually understands these things, or what level of understanding it reaches, and what kind of input it needs to best solve the task. So it's kind of an open problem, but there are many different approaches that we'll compare later in the semester. Yes?
The self-supervised model was trained only in the English
so that's a good question. The question is, so here we're showing translation into French. If this giant model over here only ever saw English and never saw French, would this work? No, it wouldn't work, right? It needs to see examples of the languages that you want to handle in whatever the task that you want to solve is. It turns out that if you download the internet, there's a huge amount of text in many different languages, but there have been many approaches that we will cover, many different models that were trained that vary the distribution of the languages that it was trained on. So for example, ChatGPT and GPT-3 were trained primarily on English language data. ChatGPT also includes a lot of code. But Bloom, which is a model that was trained as part of this giant multi-institution effort, is trained on, they explicitly had a distribution of this much English, this much this much this, and they made it more diverse over different languages. So it's still unclear what the best way to handle that is.
Would it need to be trained on direct ties of words between those languages?
That's a good question. So in order for it to do translation, does it actually need to be trained on parallel data? That's the term for what we were saying, which is these examples of this is the word in English, this is the corresponding word in French. It's very hard to answer that question because all of these models are trained on such huge amounts of text that I am certain they have seen many instances of these kinds of parallel pairs. However, they are not actually explicitly supervised on any parallel data. I think there has been a lot of work on completely unsupervised machine translation that shows that if you just have two language models in different languages, you can still do translation to some degree based on just similarities of words in the vector space that they've been represented in. So I can't answer that question with 100% certainty. All right, let's move on to less interesting things, which is the n-gram model that we'll be talking about today. So before we get to that, let's just talk about this task in a little bit more formal manner. So language models, so far we've been talking about them as predicting the next word given some input text. That is also equivalent to computing the probability of a piece of text. So we obviously see more use of the kind of conditional probability view of language models, where we are trying to get an estimate of the probability of the next word given all of the words before, because we can use this to generate new text, right? But it's still very useful to just compute the probability of any given piece of text. So for example, let's say I'm doing machine translation and I have a system that can give me multiple candidate translations of any given input sentence. And so I want some way of ranking those translations to see which one is the most plausible. If I had two candidates, I flew to the movies and I went to the movies, obviously one of them would be much higher probability than the other, right? No one is flying to the movies, I suppose. In speech recognition, this is another task where it's similarly important, right? You might have multiple candidates of what was actually said. So it could be either I saw a van in this example or eyes of an. So those sound similar, but obviously one is more probable than the other. So a language model is useful of computing this joint probability of a piece of text. And of course, this is also useful in the conditional form where you want to know what is the probability of the next word or the next couple words given some text that's already been provided. So like Google autocomplete, your email autocomplete, blah, blah, blah. These are all just language models at the end of the day. So just to summarize, if our goal is to compute the probability of a piece of text, so here, let's say our text is capital W, it's formed by these words, W sub 1, W sub 2, W sub 3, we can actually break this task down into predicting the probability of each word in this text given all the words that came before it. And we call a model that computes either the probability of the overall text, W, or any conditional probability of word n given all of the words up till n minus 1 that came before it. These are both called language models. You don't necessarily need to have a model that can do one or the other, but both of them are, yeah, go ahead.
Would say the example of the second one, the probability of W given 1, 2, 3, and 4. That statement just written there doesn't seem like it accounts for positioning of the previous words either, right? But I assume like literal sentence structure or something.
I see. So the question is related to the order of the words in this prefix. So we have kind of shortened the notation here. You can imagine that this actually means this W1, comma W2, comma W3 means the first word is W1, the second word is W2, the third word is W. So the order is encoded there. Yeah. The notation is usually simplified like this, but. Okay, so let's take a look at how these two things can be equivalent with most language models. I'll get to you in a sec. So first, we have, let's say, an example, its water is so transparent that. And we might be interested in computing the probability of this phrase. So how can we do this? One way is just to decompose this joint probability into the product of conditional probabilities using the chain rule. So this is something that probably all of you have seen before in any probability class. It is also the core mathematical construct behind a language model. So I probably will just do better at explaining this with actual words, but essentially if you have a joint probability distribution over a set of random variables, you can factorize this into the product of conditional probabilities like you have here. P of A, B, C, D equals P of A times P of B given A times P of C given A and B, and you can extend this out to an arbitrarily long sequence here. So if we extend this to the actual words in a piece of text, if we have a piece of text which has words W1, W2, all the way to Wn, this probability is equal to the product of the probabilities. So here we can see probability of its times the probability of water given its, so its came before water, probability of is given its water, probability of blah, 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 right? So you can do this for any text, just break it down into these product of conditional probabilities. So some terminology in your homework 0 and for the rest of the semester, we will refer to the previous words that came before the word that you're currently predicting as a prefix. And a lot of this class will be focused on just how do you model the prefix. What is the best way of extracting all the useful information from this prefix such that you have the best estimate of what the next word could be. And you can go, there's a huge range of models. Today we'll talk about a very simple one that involves no training at all and just involves counting and dividing basically occurrences of words and phrases. Something like ChatGPT is much, much different than that, and actually trains a specific model to represent this prefix in a dense, low-dimensional vector space, and then predict the next word based on that representation. All right, so let's start with some very primitive language models. One way I could estimate this conditional probability, P of the, given its water is so transparent that, is I could just simply count two things, right? I could count up all the occurrences of its water is so transparent that, and then count up all the occurrences of its water is so transparent that the, and I can just divide these two things, and then I have this probability, right? It seems pretty straightforward. I could just count up these things in a huge corpus like the internet, and maybe I'm done. That's a great language model. Are there any problems with this approach?
There'd be some words that would follow that which would never make sense to follow that there.
So let's say, yeah, sure, there might be some word that never follows, in which case maybe I have a count of 0, so I have no probability for that. So maybe that's not a big deal.
The time cost itself, because you mentioned people looking over a giant corpus of data.
Yeah, so there are definitely, this is a very expensive approach, right? Because I haven't specified how long any of these sequences are, right? What if I have a 5,000 word long sequence? Now I actually have to keep track of counts of every single 5,000 word sequence that could be produced in the entire internet, right? And what's more is that it's, there are other problems, not just the expense. Does anyone have any other ideas?
This formulation is sort of agnostic to the order of the words.
No, sorry. So assume that this is the order is preserved in this these counts. So you're only counting when you only get a count when its water is so transparent that occurs in that order in your corpus. Yeah.
Is there a finite number of prefixes? Like, you said an infinite number of prefixes?
Yes. So this is the biggest problem, right? Is that you could have an infinite number of prefixes, and you will have a very, very sparse set of counts at the end of the day, because the vast majority of those prefixes are never going to be observed, right? So as an experiment, you can imagine, let's say I have a giant book, right? Maybe it's 50,000 words long, and I change one word of that book to something else. Now that's a completely different count if I'm interested in the probability of some 50,000 word long sequence. So this is a terrible approach, right? You run into just huge issues with sparsity, lack of data. Regardless of how much data has ever been written on the internet, you don't have enough to estimate all of these probabilities, just because the counts get very, very sparse as you increase the length of the prefix. So the n-gram model is directly following from this observation, and how can we get rid of this kind of sparsity problem but still have this simple count-based approach. And it utilizes the Markov assumption, which I'm sure many of you have seen. So if we wanted to compute the probability of the, given its water is so transparent that, let's assume we won't be able to compute this exact probability because we don't see enough occurrences of its water is so transparent that, the prefix in our corpus. We could kind of approximate this probability by instead chopping off everything of this prefix except just the last word, right? So now it's much more likely that I will observe occurrences of the word that in my corpus, and I can look at all of the words that follow the word that, and probably I have a lot of data enough to have some sort of reasonable estimate of this probability. Of course, this is bad for other reasons, right? What is a reason why this might be bad? Other languages. Okay, yes. So some languages it might be hard to even split the words in this manner. Let's assume we're just looking at English, though. There's still big problems.
You consider this as a Markov chain, then you consider like other words, then the pronunciation increases.
Yeah. So if you wanted to have more words in your prefix, this is still expensive. But let's assume that we are sticking to this case where we just have one previous word. Yeah. Exactly. So you can think about it in terms of constraints, right? Like I have a lot of constraints on what the next word is because I know that this prefix is talking about water and transparent and things like that. If I get rid of everything except the word that, I no longer know that water was mentioned or transparent, and there's a huge range of words that can follow the word that, right? So I'm losing my precision in what I think the next word is. So in general, as I have a longer and longer prefix, I'll have more constraints over what the next word can be. And by applying the Markov simplification, I kind of lose a lot of information just because it got chopped off of the prefix and is no longer affecting my estimate of the next word. Going back to your point, one way to handle this is to extend the length of the prefix. So maybe it's not really satisfying to just consider the previous word only. What if I consider the previous two words? So here I get transparent that. The word transparent is definitely kind of infrequent and probably gives you a lot more constraints over what the next word should be, but it's still kind of ambiguous what context this prefix appeared in, right? That will always be a problem with this kind of approach. But it makes this approach of counting and dividing actually tractable because regardless of where we choose to chop off our prefix and how many words we choose to allow, we can count all occurrences of strings up to that length and then just use this simple count and divide rule to get the conditional probabilities that we want in our language model. So let's take a look at the worst possible model, which is the unigram model. So when we are talking about an n-gram model, the n refers to the number of total words that we are counting. So in a unigram model, you can see that we approximate this joint probability as just the product of basically the frequencies of the words in that text. So there's no prefix that we're conditioning on here. Okay, so let's take a look at what happens if you just count up. So just to be clear, a unigram model, you can get one from any piece of text by just, for each word, the probability of that word is the frequency of how often it occurs in that text, right? So if I had, what is this example? Its water is so transparent that, and I want to predict the next word, the conditional probability of the given its water is so transparent that, in a unigram model, this is equal to the probability of the, right? With no other context, because it is only considering one word. So basically, this is equivalent to the frequency of the word the in the data set that you estimated that on. So to be clear, in a unigram model, regardless of what context you have, this probability of the is going to be the same. So it's a terrible model. And you can see that in the sentences that are generated from a unigram model. So if you just generate text from a unigram model, it's not grammatical. You can see that there's a lot of common words like an, of, the, and, the, so on. Why does this make sense? Why would you expect to see this? That's true. Those are just by far the most frequent words, right? So that's why you see them over and over again. Yeah.
Why are there so many commas?
The commas are just there to separate they're not actually produced. Although comma would probably be a very frequent word as well. Yes?
So why does the unigram model not output the most frequent word all the time?
So that's a good question. It's related to this question in the yellow box. So how do we even generate text from a language model? What does that mean? So there are many different ways that you can do this. And the process of generating text from a language model is called decoding. So let's take a different example here. Let's say we have the prefix students opened there, and we are trying to generate the next word. So in any sort of language model, what you will get is a conditional probability distribution, right, of what is the next word given this prefix. And that distribution, how many possible options are there for the next word? It is whatever you have defined your vocabulary to be, right? So for sake of example, assume that we have a distribution over all of the words in English from A to zoo. So this is not obviously an exhaustive vocabulary, but let's say we have thousands and thousands of words in this vocabulary. So any language model is going to give us a probability distribution over this vocabulary, right? So there'll be some probability of A given this prefix. It hopefully should be low because it doesn't make sense in this context. There will be some probability of zoo, students open their zoo. This also doesn't make sense, but depending on your language model, there might be some probability on every single word. But the words that have higher probability in this context, like books and laptops, you would hope to choose to actually predict next, right? So let's say we wanted to generate the next word. So we have a prefix, students open there. We have a language model that has produced this distribution of the next word, which is over the full vocabulary. What are some ways I can choose a word to predict next, given this distribution?
Just randomly generate a number?
Okay, let's say I randomly generate a number. What would I do with that number? Just pick the word associated with that number?
Yeah, use it like an index, essentially.
Okay, so let's say I have 10,000 words. I randomly generate the number 900, and I pick the word that is 900th in this vocabulary to be produced next. This is, not actually using the probabilities that are produced by this language model, right? So it might be a useful baseline, but it's not going to give you a grammatical or meaningful sentence.
You could just create like a number between 0 and 1 and see where it goes, like the probability.
Mm-hmm. So that seems similar to what he suggested.
No, because it's where you will be using the distribution, like indexing probability.
Oh, I see. Okay. Yeah, you could do that as well. And maybe, yeah, so then in that case, you would sample words that are more likely more often. Sure. So what you are suggesting amounts to sampling from this distribution in proportion to the probabilities of the words.
Yeah, it's basically doing like this inverse probability thing where you kind of reflect the uniformity of 0, 1 to like across the, I don't know how to explain it, but across like the probability.
Yeah, but in any case, you're suggesting that we should sample from this distribution where words that have a higher probability are more likely to be sampled, right? So this strategy is very commonly used to generate text from language models. It is used in many variants for things like ChatGPT and GPT-3 as well. What's another way that you could choose to generate text?
I think we were using a markup machine, so we could do something projection-based sample and have like an NCFC, which would be slightly better than just straight up doing regular sampling.
Yeah, you could do that. That is probably way too complicated for this particular setting. Any other like simple ideas?
Just pick the biggest.
Yes, you could just pick the word that has the highest probability. So in this case, you could just ignore any sort of randomness and say, I will always just predict the word that has the highest probability. Now, coming back to your question, if you did use this strategy, then you would expect the word, like say the, which is probably the most frequent word, to just be produced over and over and over again from this unigram model. If, on the other hand, you're using a sampling-based strategy, then you might expect to see something like this, where the words that you see are sampled in proportion to how frequent they are in the text. So we will have probably a couple of classes on different decoding algorithms that are either kind of deterministic or sampling-based, or model-based, which are quite different. But this is a very important concept, so it's important to understand how you can kind of interact with this conditional probability distribution to generate a word. So we've so far talked about just generating one word. If we wanted to generate, so let's say we are using the simple strategy of selecting the word that has the highest conditional probability. So in this case, we select books, so we get students open their books. How do I generate the next word? How can I generate a longer piece of text?
Do you use that new one as a prefix now?
Yes, exactly. So now I have a new prefix, students open their books. I put this into my language model, get a new conditional probability distribution of the next word, and apply the same strategy to that. So this is how any sort of text generation process works. You do it one word at a time using the conditional probabilities that you're getting as you update your prefix with words that you've already generated. Yes?
So let's say the first one was already bad, would that make all the other ones even worse than that?
Yeah, this is a great question. So let's say I sampled zoo. So I said students open their zoo. I guess that's actually not that bad. Whatever. So anyway, let's say I got this. There are sampling strategies such as beam search that will allow me to consider many different candidates instead of just one. So I can at some point decide to not use this particular generation if I find better ones. But in general, all of the ones that are being most used today are sampling based, where there's only one hypothesis of the generation throughout. So yeah, if you make one bad prediction, you can't really recover from that. And actually, your subsequent predictions will probably be much worse also. All right. So let's see what happens now, coming back to our n-gram model. We've so far just talked about a unigram model. A bigram model is a model where instead of considering no prefix at all, as in a unigram model, you consider just the last word. So this right here, the probability of the given that, is a conditional probability you would get from a bigram model. You can see it's called a bigram because you're measuring the probability of this two-word sequence here. So you're counting the occurrence of this phrase, this two-word phrase, that the, in order to compute this probability. So you can see in this slide here that if you're sampling from language models that are n-gram models of different prefix lengths, so 1, 2, 3, 4, the text that you generate gets more and more fluent as you increase the length of the prefix that you're considering. So the unigram model is terrible. This is just like, it doesn't make any sense. In the bigram model, you see some like minor grammar is a little better, but it still makes no sense. In the trigram model, now you're considering the last two words in the prefix. Here you see, therefore, the sadness of parting, as they say, it is done. Obviously, it doesn't make sense, but it's at least more grammatically correct. And then in a four-gram model, I will go seek the traitor, a great banquet served in. So these language models were trained on all of Shakespeare's plays. So it's a very small data set in order to estimate these probabilities. But you see, like, as you increase the order of the n-gram model, the prefix length, you're getting more fluent text. Yes.
So in general, is there like a magic number, or is it just a situation?
So the question is there an optimal number of n? It depends on the situation, like how much data you have is most important. If you have a lot of data, then you can get better estimates for the longer prefixes. If you have like the Shakespearean corpus, then maybe you shouldn't go past a certain number, but it just depends. So I think the largest n-gram models that like Google had trained in the past were, I think, 10-gram models, maybe a little more than that, but definitely not anything super large. Yeah. Yeah.
Is there anything apart from data which can help us get that number?
So I will talk, I think, hopefully now about how you can actually evaluate the quality of a language model, which can give you an empirical way of measuring which n-gram model or which language model is better. So let me hopefully do that. But first, I just wanted to give the inherent limitation of n-gram models just to make it more clear. The biggest problem of these models, other than the sparsity as you increase the prefix length, is that at some point you're just not going to be able to handle long distance dependencies due to the Markov assumption. So if you have a sentence, the computer, which I had just put into the machine room on the 5th floor, crashed. Crashed here is, of course, connected to the computer, which is, like 12 or 13 words in the past. So regardless of if I use the n-gram, the bigram, trigram, fourgram, so let's see what would happen if I used a bigram model. I would just get the word floor as my prefix. 5th floor with the trigram model, the 5th floor. None of these have the key information of the computer is the one that crashed, right? So regardless of, even if I have a 10-gram model, I won't really know what it is that is doing this crashing. I might have some idea if I get like machine room, but still it's not very specific, right? So the models that we'll talk about next week are, and in the course of the next couple weeks, have much better abilities to deal with this kind of long-range dependencies. All right, so I think we've already discussed basically how you compute these conditional probabilities with an n-gram model, but just to make it clear, we are using, so we'll have like a training data set. So this is some text that we've collected from a source like let's say the internet or Shakespeare's plays. And then we'll set to work counting all occurrences of, let's say, 2-word phrases that occur in this data set. So if I wanted to have the conditional probability of any word I given the previous word I minus 1, all I have to do is divide the count of that 2-word phrase, wi minus 1, wi, divided by the prefix, wi minus 1, right? This is the same rule that you would use for a trigram model. You just are extending the prefix lengths in your count. And you have to keep track of a lot more things as you increase the order. So, simple example. This is probably the only class where we'll just be like counting things and dividing them. But let's say I have these 3 sentences. I am Sam, Sam I am, I do not like green eggs and ham. You'll notice that each of these sentences starts with a special token. This is called the start of sequence token, and ends with another token, end of sequence. So we'll talk later about why these 2 tokens are very important for any language model, not just an n-gram model. Intuitively, if you think about the end of sequence symbol, we would like to know when our language model should stop generating a piece of text, right? Otherwise, it can just predict the next word forever. So when it assigns a high probability to the end of sequence token, that's when something like ChatGPT stops producing text. You don't see it, but that's what's happening in the background. So let's get back to the simple bigram model. If I want to know what the probability of I, given the start of sequence symbol is, I can just count up all occurrences of the prefix, the start of sequence symbol, so I have 3 of those, and see how many times after the start of sequence symbol was the next word I, right? So in this case, I have 1 positive count. In this case, the next word was not I, and in this case, it was I. So 2 of the 3 times I observed I after the start of sequence symbol. So my maximum likelihood estimate for this is going to be 2/3, this probability, which is obviously kind of an artifact of having such a small data set, is these probabilities are very high. Similarly, let's take a look at another example. this is how many times after seeing the word Sam do I produce the end of sequence symbol. So I observe the word Sam 2 times. After the first occurrence, I do observe an end of sequence token. After the second occurrence, I don't. So this probability is 1/2. Okay, so let's do this as an exercise. What is the probability of Sam given the start of sequence? 1/3. Okay, so I have 3 start of sequence tokens. Only after one of them do I observe Sam, so this probability is 1/3. Great, so you could do this for all of the different combinations that you have here and that you observe in this data. And any other bigram, any other 2-word phrase that does not occur in this data set is marked as 0 probability. So even if it is valid, in general, you don't have data for it, so its maximum likelihood estimate is 0. Okay, is that clear? All we're doing for these n-gram models is counting and dividing. There's nothing fancy about it. Okay, so at this point, I just wanted to talk about some terminology that will be very useful moving forward in this class. So when we talk about words or items in our vocabulary, let's say I have 10,000 words in my vocabulary from A to Z. I will refer to each item in the vocabulary, each unique word, as a word type. And any word type can occur more than once in a piece of text, right? So in this, let's say I had I am Sam, Sam I am. I used the word Sam twice. I used the word am twice. So if I want to be more precise, I can say I had only 3 word types in these 2 sentences, but I had 2 occurrences of the tokens corresponding to these word types, I, am, and Sam. So a token is any occurrence of a word type in the text. A type refers to a unique word in the vocabulary. Is that clear? All right. So, I also wanted to show a little bit of a demo with a larger scale corpus. So Google has this n-gram viewer. I don't know if some of you have seen this, but it lets you search for the occurrence, the frequency of many different phrases in the Google Books corpus. So all of the books that have been digitized by Google, you can search through, and it's actually pretty interesting because you can see, like, maybe I can make this bigger, from the year 1800 to 2012, how the occurrence of certain phrases and words has changed over time. So, for example, if I looked at the phrase ordered a pizza, you can see that people were not ordering pizzas until like 1970, and then people ordered a lot of pizzas. If I can compare this, right? So I can look at ordered a, what else is something I can order? Car. All right, so I don't know what this means. I guess ordered a car is kind of strange phrasing maybe, but a cab, okay, yeah, sure. Ordered a cab. Okay, it seems similar to ordered a car. Any other ideas? Ordered a sandwich, how about that? That seems... Okay, so clearly a pizza is more frequently ordered in 2013 than any of these other things. And you can see these relative frequencies. So Google is not going to report the exact count of each phrase, which would allow you to, get an actual probability that you could use to potentially generate if you had API access. But you get these relative frequencies. So if I had an n-gram model trained on Google Books, it would assign a higher conditional probability to pizza given ordered than sandwich, car, or cab. Although in 1912, this would be different. So yeah, this is pretty interesting. There's actually quite a few papers in digital humanities that use this Google n-grams corpus to make some interesting conclusions of the change of language use over time and how that corresponds to social situations going on in the world. All right, just wanted to show that. Let me go back to this. So in your reading, you probably saw this, a bigger example from the Berkeley Restaurant Project. So these are just like kind of conversations about restaurants. I'm looking for a good place to eat breakfast. We can take a look at this as a like little larger scale bigram model. So generally, if you're doing n-gram modeling, you're going to form a table that let's say the rows here correspond to the prefix and the columns correspond to the next word. So in a bigram model, the prefix is one word long and the next word is obviously one word. In a trigram model, these rows would be replaced with bigrams, so two-word phrases, right? And of course, you can see that this table gets exponentially bigger as you increase the order of the model. So if you form a table like this, the table is basically encoding the number of times want occurred after the word I, or the number of times the word eat occurred after the word to is 686. Spend occurred 211 times after to. So how do I convert this into a table of probabilities instead of counts? What would I do? Yeah, exactly. So I would just sum to get the total number of occurrences of the prefix and then normalize every cell by that count, right? So this example that they show is just a subset of obviously a much, much bigger table. So if you actually compute these probabilities using just the information you have, you won't get these numbers here. These numbers are reflective of the overall bigram table. Yeah, you can see that the probability of want given I is 33%. The probability of, let's see, are there any interesting ones? Oh, I think I have these on the next page. So anyway, you can use this probability table then to compute the joint probability of an entire sentence, right? So if I want to know the probability of I want English food, this is just a product of all these conditional probabilities, each of which can be found from this table that I obtained by simply counting and then dividing. All right, so there's a question down here. These probabilities get very tiny when I have longer inputs, right? I'm just multiplying these different fractions together. The number is getting smaller and smaller and smaller. You can see that this probability of the sentence is 0.000031, right? That's very small. What happens if I have a 5,000 word long text? This probability is probably going to cause some errors because it's so small. So the way we handled this is, I'm sure lots of you have encountered this, is just we replace this product of probabilities with the sum of the log probabilities, right? So let's take a look at how this works. If I have this sentence, this is an actual sentence from some movie review corpus. I love, 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 love the movie. The probability of the sentence is like 5.9 times 10 to the negative 7, so it's very low. The log probability of this is minus 14, so this is much more tractable to work with. In any implementation of a language model, regardless of what type it is, it will always be working with the log probability. And in the models that we'll be looking at next week, we'll be talking about the negative log likelihood, which is actually a positive number that you can minimize, which tells you how well the model is actually doing. So let's step back and take a look at what is actually encoded by these probabilities, because I think this is very useful in explaining why language models pick up some understanding not only of the language but also about the world that is represented by their training data. So on this restaurant corpus, you can see that the probability of English given want or Chinese given want is notable. This indicates that the model has encoded that people like different types of cuisines, right? If you see want, they want a type of food. So there's some sort of world knowledge encoded here. You can also see elements of grammar that are encoded. So the probability of to given want, so this phrase want to, is very high, right? And this is what you might expect in such a corpus. The probability of food given to, like, I want to food or something, that is 0, which also encodes some sort of knowledge that this is not an acceptable next word given this context. Similarly, the probability of want given spend is also very low because that doesn't make any sense. The probability of I given the start of sequence token is very high. That also makes sense because many sentences are likely to start with I, especially if these are reviews written by people about their own experiences. So you can imagine extending this to a much, much more complicated model. You can see it's encoded all sorts of world knowledge, knowledge about the language, and also even some sort of reasoning abilities, which we will look at later on. So if you're interested in using n-gram models for anything, perhaps as a baseline model in one of your projects, there are really good toolkits that compute these count tables efficiently and apply all sorts of smoothing algorithms to make them functional that you can check out at these links. Okay, so for the last 20 minutes, I want to talk about how to evaluate a language model. So before I do that, I just want to give an overview of the general train test paradigm in machine learning for anyone who's not familiar, since we don't have prereqs. And then I will talk to you about how we actually use this to evaluate how good a language model is. So let's take a look at this example. So I am going to estimate a bigram model on every single New York Times article that's ever been written. So what do? I take all of this text and I convert it into this table that we just saw, right? So I count up all occurrences of 2-word phrases, then I normalize by the occurrence of every single word prefix, and I have these conditional probabilities, right? So now I want to know how good my estimate of these conditional probabilities are. So the key insight is that we want a good model to also assign high probability to text that it was not trained on, right? That we did not use to obtain these counts. So if the model could only assign a high probability to text from the New York Times and not high probability to text, say, from the Washington Post, that would be kind of bizarre, right? That would indicate that perhaps this model has overfit to the training data and has not learned anything actually important about the language itself, but rather has just learned about its training data. So what we might want to do is evaluate our language model by computing the probability of some held out text. So some test sentences or text that the model did not see when we were counting and dividing, right? So if I use the corpus of the New York Times, the Washington Post as a test set, obviously we would want the model to still assign high probability to these articles. So does that actually happen is the question. The key insight here is that a good language model should assign high probability to naturally occurring text that it has not seen before. Does that make sense? Yeah. Yeah, so that's a good question. What if the test set includes a new word that was never observed in the training set of this language model, which means there is no entry in the table that includes this new word, which means we can never compute its probability, right? So in n-gram modeling, there are ways to deal with this where you can replace all words that occur below some frequency with some special like unknown or rare word token, and then you can model that probability directly. With more complicated models like, say, ChatGPT, this just doesn't happen at all because the vocabulary not only includes words, but it also includes subwords and characters. So at the end of the day, you can always split a word that you've never seen before into the characters that make up the word and model that. So we'll talk about that much later on, but there are ways to deal with these cases. Yeah.
So in other branches, I've seen people do like the train, validation, and held out test set.
Yes.
Is that a thing in NLP or no?
Yes, so I just skipped over the validation set, but in your projects and in everything, you should have a validation set. It's especially important for more complicated models because there are many different configurations of the model that you might want to try out. So for example, for ChatGPT, you might want to observe whether adding more layers to your model is going to improve its probability of the held out data, right? So you can use the validation set to iterate over different configurations. Pick the one that has the highest, that gives, say, the highest probability of the validation set, and evaluate that once on the test set. So yeah, that's a general paradigm in machine learning.
What would you use to determine what's a high enough probability with respect to the training data? Is there specific ways to say, 75%, a probability of 75%?
Well, this is a good overall question is, in any language model, the probability of the training data will always be higher than the probability of the held out data, right? So how do you know if a model is actually good? Knowing that the probability it assigns to the Washington Post will be lower than the probability it assigns to the New York Times. In general, you use this to compare different language models to each other. So for example, maybe you have a unigram, bigram, trigram, fourgram model, and you evaluate all of those on the Washington Post, and you observe that the bigram model gives the highest probability out of all of those four. You would say that that is the best language model that you have. You don't objectively know what is the maximum probability that can be assigned, because it's certainly not one, right? I could say order to blank, and there's many plausible options that could go into this, right? So you don't know what is the upper bound. You're using it mainly to compare models.
So it's mainly like a relative score.
Yes, that's right. Okay, so very important, just like in any other machine learning task, you cannot allow any information or sentences or text in your test set to leak into your training set. If you do this, you will artificially inflate the probability of your test set, which will cause you to draw erroneous conclusions. So do not train on your test set. Do not do this in your final projects. Be very careful about your splits that you're creating. Make sure there's no overlap. As we'll discuss later in the semester, it's actually quite difficult to do this for many NLP tasks, and so you should take some care. Yeah.
If I try to train multiple versions of my model, like I keep evaluating on the same test set and then I pick the best model, is that also false?
Yeah, so that's going back to his question. That's why you should keep a validation set, so you can evaluate many different times on the validation set. In any of these cases, you will end up overfitting to that fold that you're evaluating multiple times on, but hopefully it's not too bad. That's the general idea. Okay, so I've so far kind of just hand-waved this example, this evaluation. I've just said, we want a model that assigns a high probability to the test set. The actual evaluation metric that we use is called perplexity, and it is basically doing this. It's just a very simple function on top of the probability of the test set. So we'll go to the definition of this here. You can see that the perplexity is the inverse probability of the test set, and it's normalized by the number of words in the test set. So this way you can compare across many different texts. If you normalize by the number of words, you're basically looking at the average token level probability of the next word, and you want that to be high. And so the perplexity also inverses this. So you can see it's a direct function of the probability of the test set, where the probability of the test set is P of W1, W2, W sub n. So minimizing the perplexity, because it's inversing the test probability, is the same as maximizing the probability of the test set. So you might be thinking why we use this perplexity instead of just measuring the probability of the test set and comparing models that way. The answer is kind of historical. There are some kind of information theory interpretations of perplexity that can be useful. So for example, let's say I have a setting where I have a sentence that consists of random digits. So there's 10 digits, right? 0 to 9. So if I wanted to compute the perplexity of this sentence, I would, going off no other information, this is a random digit selection, each digit in the sequence has a probability of 1/10 to be generated, right? Let's just assume there's no dependencies on previous words. So in this case, the probability of generating the overall sequence of length n is 1/10 raised to the n power, right? Just the product of these individual token level probabilities. And then if I compute the perplexity, I raise this to the -1/n power, where n again is the length of the sequence. And so eventually what I get is just 10. The perplexity is 10. And what this means is you can interpret perplexity as kind of the branching factor. So at any point in the sequence, how many options on average did I have that were equally likely to be produced? So in this case, there was no information other than I knew I was choosing from one of 10 digits. So at every point in the sequence, I had 10 equally likely options to choose from. If I had a better model, and maybe I was using natural language, in some cases, I might have only one viable option of what the next word is. In some cases, I might have 10 or 15 or 500, right? So perplexity is basically just showing the average branching factor of the model. How many equally plausible options were there at any given point in time? So you want a model that assigns a lower perplexity to the test set, because that means the model sees less possible options for every single word in the test set as equally likely, which means it has a better handle of what the content of that text actually was. And so perplexity is the metric that is used to develop models like ChatGPT. So when you're developing a language model, perplexity is the main metric that you use. You make a bunch of changes, you add more data, you do all sorts of fancy things, whatever you want. At the end of the day, you will be evaluating in general by which model gave you the lowest perplexity on some held out data. In practice, I talked about the log probabilities. We are using the log probabilities to avoid these underflow errors. So perplexity becomes the exponentiated negative log likelihood averaged at the token level. So this is probably a fairly complicated sentence for those of you who are unfamiliar with these things. But I'll just say that if you're training a language model, or if you're training any sort of classifier and you have experience in machine learning, you're probably using the negative log likelihood as your training loss. And the perplexity is just that loss exponentiated. So it's quite straightforward to compute given what your language model is already outputting. So again, lower perplexity is a better model. You can see that this we trained on 38 million words from the Wall Street Journal, tested on 1.5 million words that were not included as part of the training set. A unigram model is giving us a perplexity of 962, meaning at any point there were like 962 equally likely options. So note that this unigram model is not giving us a perplexity that is of the size of the vocabulary, right? Because it is frequency weighted. A bigram model is really cutting down on the number of equally likely next words. You get 170 and 109 with a trigram model. That said, these perplexities will not continue to decrease like this. If you go up to like a 13-gram model, there are severe issues with sparsity that will cause this to increase dramatically. So going back to someone's question here, what happens if you don't observe a particular token in your training set, but then it appears in your test set? This is a much bigger problem than you can imagine. So it even expands to assume you've seen all of the words before. You certainly haven't seen all two-word combinations before in your training set, right? So even in Shakespeare, right? Shakespeare wrote 884,000 words total in his plays. his vocabulary was about 30,000 words. So he produced 300,000 unique bigrams. Bigram types means unique bigrams. But he could have produced 844 million possible bigrams, right? So 99.9% of possible two-word combinations that he could have used were not used in his place, right? Most of these make no sense, right? These bigrams, they're just any sort of word followed by any other word. But there's still many combinations that are valid in English that Shakespeare did not produce. And these will have zero probability in your bigram table. So, this can crop up in many cases, like in the training set, you might have denied the allegations, denied the reports, denied the claims. In the test set, you might have denied the offer, but if you didn't observe this at all, then it'll have a probability of 0, even though it's a very, very plausible phrase. So one way that you can fix this problem in n-gram models is to apply what's called as smoothing. And 5 years ago, we might spend a whole lecture on smoothing. Now we're talking about it in like one slide at the end of class. But it's actually quite clever, the many different smoothing algorithms. Essentially, what they do is they steal some probability mass from the observed bigrams or n-grams that you see in your training set, and they distribute that mass that you stole over all of the unobserved items in the table. So if I saw allegations a lot and reports and claims and requests, but I never saw attack or man or outcome, I can take this much probability away from all of the things that I actually have observed, and then distribute them in some fashion to the previously 0 probability bigrams. And so there are many different methods of determining how to distribute this mass across the unobserved items, which we will not talk about here. Okay, so I see there's a question in the YouTube. Assigning high probability on the test set is considered another method of evaluation. If you assign high probability to the test set, that is equivalent to assigning low perplexity to the test set. So it's the same sort of evaluation. Do you calculate perplexity on the training set? You certainly can. It's usually kind of useful to do that, so just so you can make sure that the model is assigning a very low perplexity to the training set. But in general, you're more interested in the test or validation perplexity. Yes?
Can you still keep some of those here if you want?
Yeah, you could. It depends on the smoothing method. So some of these you might determine as they would never be produced. They're not grammatical, so I will not distribute probability mass there. But yeah, we just won't talk about any of these methods because the more recent neural network-based language models don't really suffer from these issues. Okay, other questions? Oh, perplexity and surprisal. Yeah, they are very related. I think the surprisal isn't it, I forget the actual equation, but it's something similar that's just a function of the probability of the next word, right? So all of these can be computed just from the probability of the next word. Yeah, perplexity is generally assigned over the entire text, not just one prefix. So it's basically averaged over the entire, like the average probability inversed over the entire test set. Other questions? Yes. How does language models, how do they deal with what? Concept drift? Oh. Yeah. Yeah, that's a great point. So concept drift, I imagine you're referring to like the meaning of some phrase changing over time or with respect to different events. This is a big problem even with the state-of-the-art language models that we have today, right? So the language model is estimated at one time, right? So I could compute this bigram count table today, but there could be new words that are formed tomorrow or new phrases, or phrases could change their meaning. that I just don't have any access to because I only have access up till today in my training data set. So one solution is just to re-estimate that count table every single time, and maybe you can track the change in meaning, but that's very expensive, especially for more complicated models like, say, ChatGPT, which might have taken months to train in general. So we'll talk later in the semester about methods that allow these language models to access kind of up-to-date information or time-sensitive information that can allow them to make sense of this kind of drift without actually updating the entire model itself. But it's an open area of research. All right, so next week we will start our a couple lectures on neural network language models, which we will continue to build on in terms of complexity to transformers. So see you then.